Thank you. I'd like to thank Rohini for thinking about this because I think this is perhaps one of the most apt meeting for physicists and mathematicians to talk together. So thank you again for asking me to talk here. So after having had all these wonderful talks, I'm almost ready to go home, in fact. But so what I want to tell you today is the importance of the role that Noether's theorem has played, or the implications that it has had for the development of particle physics, or the theory of particles and interactions among them as we know it today. So this was shown a little bit, but I thought I found an English translation of the paper, which was presented by Klein to the, I think I have somewhere a full form. No, I don't have. This was Gesellschaft something, that Königliche Gesellschaft. So it was some sort of an academy presentation. And this is a translation of her abstract, in fact. And the abstract, as was already discussed, is so clean and so beautiful. I mean, it's one of those things that you read the abstract and you really know sort of what is there in that paper, and it's sort of really amazing, I feel. So this was already told to us that she was at Göttingen, which is the longest time from 1915 to 1933, and where she worked, she didn't work with them, but she worked on ideas that were pestering them and for which they didn't have answers. So it was more like them turning to her saying that we really don't understand, you are the expert in invariance theory, and really this, she came with delivered the goods, in fact, I mean. So it's an amazing the thing, I feel. And she also gave the plenary address to the International Congress in 1932. Given the fact that not more than 3 decades before that, 2.5 decades before that, people said that what will our soldiers think if they have to learn at the feet of a woman? Given the fact that that was the kind of society in which Emmy Noether grew up, I think it's all the more, I would say, lucky for us scientists that this was not lost, as it could very well have been lost in many other cases, and we don't even know it. So this is an amazing woman, amazing contribution, and as a physicist, I would like to tell you what it contributed. So as I said, this I already told you, that this is what I would like to really emphasize, but that's not all. What I think is that at times what has happened is that after knowing and having understood the structure of standard model as we know it today, actually the theorem, Noether's theorem offers us insights into why things are the way they are. I mean, in some sense, I think Noether's theorem gives us a feel why the laws of physics are what they are. And I think that's really an amazing level of, and that's in one line one can say, is the importance of her contributions to physics. And so that's the second part, that the deep insights that are offered by this theorem, and of course many related ideas, to understand the observed structure of the theories. And last but not the least, I would also like to spend a few minutes on legacy of Emmy Noether as a woman theoretical physicist and mathematical physicist and mathematician. So I'll begin with some brief survey of Noether's theorem, though that is really not necessary, but one always likes to have one's own way of looking at things to present to friends. So, and then I will give one example of how the conservation laws, which were implied by Noether's theorem, helped postulate one of the groundbreaking contributions which began the world of weak interactions and weak interaction theory. So I have chosen it for that purpose. Then I would try to talk about something that has not been discussed too much here, and that's the gauge invariance and Noether's theorem, because theories of particle physics are indeed the celebration of gauge principle and gauge theory. and then this. So we all know here that for the past 70 to 80 years, symmetries of laws of nature have been the underpinning of the development process of particle physics, the theories of particle physics. That has been, I was telling this in the tea break to somebody, that just like you don't remember when you learned walking or when you learned talking. I think most of us theoretical physicists don't even remember when was the first time that we learned about this connection between symmetries and conservation laws. You kind of learned it through osmosis, and then somebody taught you. But this is just part of theoretical physics of 20th century through and through. And these symmetries could either be space-time symmetries, which is sort of really very fundamental in some sense, and also the internal symmetries. In particle physics, both of these have played a role. So as I said, one thing they did is that they provided an understanding of the space-time symmetries of the law of nature. What do I mean by that? That the conservation laws are some conservation laws. It told us about some conservation laws which have to be sacrosanct and which have to be satisfied by independent of the details of the dynamics. One of them is energy conservation. And this removed actually the mystery in which energy conservation was initially shrouded, and so much so that it then led to the postulation of new particles and interaction, and I will try to give you some discussion about taking neutrino as an example. Yeah?
Can you clarify on what is symmetry involved in energy conservation? Let's say there's momentum.
I am going to come to that. I am going to actually spend at least 2 slides on that. So this is, I'm just giving you a brief summary in case you lose your concentration as to what's coming up. After that, this is what I hope to convey to you. And then the second, as I said, it provided deep understanding of the observed facts about the dynamics. This I will illustrate by something that I'm not going to discuss, and I hope Loga will be discussing it, because that already this was touched upon by Professor Mukunda, that in the first, famous paper which I showed you here, it's in fact, at the end of it, she has one section on it, and that section is, her work gives an understanding of Hilbert's improper local energy conservation in general theory of relativity. The problem that was really bothering these 3 people like Hilbert, Klein, and Einstein himself is that in general theory of relativity, they couldn't find local energy conservation. Local energy conservation did not happen, and this was bothering them. And that was part of the reason why they wanted Emmy's help. So her paper actually explains that. And this is the application. So this is what I feel is that this is an understanding of the observed fact about the dynamics. That dynamically, general theory of relativity seemed to break local energy conservation, but in fact that was really not so. And this is what she actually told in the theorem. And what is interesting is that, most of the time we physicists are used to sort of taking a whole lot of observation, putting them together in some systematics, deriving some postulate of a theory from that, and then we generalize it, This is the standard physicist way. But here, this is the, at one go, she gave us a theorem which covers so many possible cases that would appear in physics in one go. So this was here where we got a tool, and we have been through the decades more or less keeping on applying it to special cases. And I like this quote from Einstein. This is on the base. This is his response to this paper. Okay, so this is for that. When he saw the text of this paper, he actually wrote and said that yesterday I received from Miss Noether a very interesting paper on invariant forms. I am impressed that one can comprehend these matters from so general a viewpoint. So that's actually, I don't know about her work in mathematics, but these 2 papers really show that it was a succinct presentation of one very general principle which can be applied in all possible situations, and we have heard some of them: classical mechanics, quantum mechanics, classical field theory, quantum field theory, what Professor Lakshmanan told us in an entirely different context, nonlinear theories. So I mean, you just see that the subject is, even after, since 1918 now, so many years, it's 100 years almost, it's still moving. It's still moving, it's still developing. So what is the major, as I see, major role that this theorem played in gauge theories? So I want to give you one slide short about how did theories of particle physics developed in the last 60 to 70 years. So how did it go? In fact, as I said in the beginning, using the theorem and the conservation laws, one actually abstracted the symmetries of equation of motion because of this theorem. Then, having abstracted those symmetries of the dynamics, for example, the U1 invariance of a theory interaction between photons and electrons. So that's called electrodynamics. Then in fact, one found that, I would give some examples of that, one found that the symmetries give some very interesting relations between scattering amplitudes, and in fact help, and one of them that I would mention is conserved vector charge in weak interaction. In fact, I will talk about it because that directly moved forward the theory of weak interactions. So I want to take examples to show you that the ideas which came from Noether's theorem actually were instrumental in developing our current knowledge of weak interaction. Then, as I said, this relationships between invariances and well-being of the theories. What is meant by well-being of theories? One of the things will be renormalization. That the renormalizability of the theory depends on these invariances. Having understood this connection for U1 theories, having understood from the conserved vector charge in weak interactions that maybe weak interactions are also described by some gauge theory, and then realizing that the gauge particles corresponding to weak interaction gauge group are actually massive, and knowing this connection between renormalization and symmetries, one was really in a quandary. At that point, some really important, so in this process, these two things happened. One was the electroweak unification, generalization of these symmetries to newer interactions, going from U1 to SU2, for example, here. And then new theoretical ideas, such as spontaneous symmetry breaking and the Higgs mechanism, to keep the well-being of the theory, this connection, intact. And then this has been going on, and ultimately in LHC has found the Higgs, has confirmed the spontaneous symmetry breaking. So now if I begin from electrodynamics and theory of photons and electrons and show you that in the 70 years, we moved along this line, and Noether's theorem and the connection between symmetries and conservations has been along the way, pushing us to the right path every moment, you realize how important role it has played for particle physics. Right now, actually, there are theoretical shortcomings of the current theory, and people have postulated new symmetries which go beyond, and those symmetries are which mix a space-time symmetry with an internal symmetry, and those are supersymmetry. So this is really how I would see the ideas have developed. So we had actually a very nice discussion, but that was mostly in the context of classical mechanics, so I think I can justify a few slides on field theory. So we heard that the least action principle, which is an action which is nothing but the time integral of the Lagrangian, gives us equations of motion. Now in a local field theory, this Lagrangian can be actually written as a spatial integral of the Lagrangian density. So this is some function, okay, of the field and its derivatives. And the action is defined as the integral of this Lagrangian density on the whole space and time. And I would call it Lagrangian in future in the rest of the talk. I will not call it Lagrangian density, but I mean Lagrangian density. Now you can say that the equations of motions of these fields are to be obtained by principle of least action, variational principle, and this gives us this Euler-Lagrange equations of motion. All right. Now Noether's theorem in this general case speaks about conserved current which is associated with a continuous transformations of the field phi. So an infinitesimal form of the transformation is, sorry, this is wrong, all right. So phi x goes to phi prime x, which is some phi of x plus some small parameter alpha delta phi of x, which is a function of x. Alpha is your infinitesimal parameter, delta phi is the deformation in the configuration space, and this is symmetry. We will say that this is a symmetry transformation clearly if the equations of motions are unchanged. Now, since equations of motion are obtained by variation of this action, if the action changes only by, if the Lagrangian changes only up to a 4 divergence, the variation of action will remain the same, equations of motion that you will get remain the same. So you say, okay, if under this transformation, the Lagrangian goes to or changes by 4 divergence and of linear order in alpha for some j mu, then that's a symmetry. That transformation is a symmetry. Now, how do you get this j mu? That is very trivial. In fact, that you substitute this phi prime x in terms of phi x and alpha delta phi x. Indeed, your Lagrangian is function of phi and d mu phi. So you can write the most general form for your change in the Lagrangian, and this is the simple expression by some rewriting, and this is your Euler-Lagrange equation. So now you see that alpha d mu, the script j mu, is equal to this guy, and therefore a small j mu, which is defined by this expression on the right hand side, is actually a conserved current, because d mu j mu, small j mu, will be d mu dl d mu phi delta phi minus d mu j mu, but d mu j mu is the same thing, therefore that will be 0. And this then gives you a Noether charge, which is obtained by a spatial integral of j0x, and as was already emphasized, this guy, which we can show that d by dt of q is 0, following d, because of d mu small j mu equal to 0, and this q is the generator of the symmetry transformation, and existence of this charge, by the way, depends on asymptotic behavior of the fields, and it's not always guaranteed. So we can find various conserved Noether charges for different transformations as in classical dynamics. Here I have taken, for example, a symmetry transformation of the coordinates, x mu going to x mu minus a mu, just space-time translation. And now if I do this, this means that the field phi x goes to phi x plus a mu, which I can expand, Taylor expand, and then I can use these formulae and get myself the Noether current, which is T mu nu equal to dl d mu phi minus L delta mu nu. Mu equal to nu equal to 0 is indeed the conserved charge is Hamiltonian, and that's conservation of energy. So, sir, this was your question, and here this is the conserved charge, which is the energy. Okay? So therefore you see, and this is exactly what was proved this morning, that the conservation of energy is associated with time translation invariance. That was done for a classical mechanical system. I have done this here for the classical field system. And for mu equal to 0 and nu equal to I, it is a linear momentum pi. So this gives me the conservation of the 4 momentum p mu and e. If I take a complex scalar field, pair of complex scalar field, treat them as 2 independent fields, and look at this phase transformation phi x going to e to the I alpha phi x, that's my symmetry transformation. The Lagrangian for a massive pair of these fields, both with the same mass, is actually very simple. And in this case, you can see clearly that this Lagrangian is invariant under this transformation. And then you can again construct the Noether current, and which up to a constant factor is simply d mu phi star phi minus phi star d mu phi. That's very straightforward. Now, in a gauge theory, when I couple this field to an electromagnetic field, then obviously what I do is that alpha is no longer constant, but alpha is a function of position. And in this case, the Lagrangian is invariant under this transformation only if phi couples to an additional spin 1 vector field, a mu, that which we call a gauge field, with precisely this form. Because when you do this, mod d mu phi square, this actually will give you terms in the Lagrangian which involve a mu, d mu phi, phi. So this actually gives you a vertex between the field phi and mu. So the form of the interaction between the field phi and the gauge field mu gets decided by gauge invariance. And if you replace, what has happened is that I have replaced this d mu by this covariant derivative, and when the field field undergoes the phase transformation and the gauge field simultaneously undergoes this transformation, then this together is a symmetry of this Lagrangian. I can now calculate the conserved Noether current, and that Noether current gets identified with the electromagnetic current density, and the corresponding charge is the electromagnetic charge. So, and for fermions, which I am not doing, the conserved Noether current would be psi bar gamma nu psi, where psi is the fermion field, here phi was my scalar field, and gamma nu are the usual Dirac gamma matrices. So you can more or less construct the Noether currents both for fermions and spin zero particles. Again, let me try to remind you, the continuous symmetry operation of Noether's theorem in this case is the gauge transformation, the conserved Noether current is electromagnetic current density, and gauge invariance implies a conserved current. Actually, gauge invariance implies a little bit more than that in quantum field theory, and what it implies is very interesting relationships between different amplitudes. And those amplitudes, in fact, allow you to prove that the theory is renormalizable. So the renormalizability of the theory is guaranteed to you only by gauge invariance, and some of the most important relationships that help you do that or analyze that, one of the most important one is called Ward identity. In this, the mu is your field. I remind you again that if I am looking at a local transformation on the field phi, I need to introduce this additional gauge field. I know the interactions of this gauge field with field phi through this term. That's the only gauge invariant way. And now, if I have fermions, for example, again, I will have this form of the interaction. The J mu is this current and A mu is the field. Now, in a quantum theory, if I want to, for example, calculate amplitude for any process where there is some initial state and it emits a photon and goes to a final state. So I don't know, I don't care which theory I'm calculating at this point, but any theory which is electromagnetic in nature. Then this, in fact, can be computed in terms of this matrix element of this current. I don't really care at this point to calculate this matrix element, but what I notice is that right now we know that d mu, j mu is 0 in classical theory, I showed you that. But if this is true also in the quantum theory, which it has been shown to be true, then we actually get k mu, m mu is equal to 0. Because d mu, j mu is 0, you integrate by parts, and this gives you k mu, m mu equal to 0. And this particular relationship is the simplest form in which it is called Ward identity. This was first recognized by Ward, and what is the use of this? It's a consequence of gauge invariance and current conservation. That much we notice. But what is the use? The use is the following, that in general, a photon has only 2 degrees of polarization. You take an electromagnetic wave, it has only left-handed or right-handed, or X and Y, only 2 polarizations. On the other hand, the field mu has actually 4 independent degrees of freedom. So we have an overdetermined system. Actually, that has a problem. So in fact, what happens is the Ward identities and gauge invariance actually ensure that in any physical process, only the physical degrees of freedom contribute. So that is actually the beauty of this exercise. So these Ward identities, which encapsulate the essence of gauge invariance, they are essentially the result of the stating the current conservation. And that's Emmy Noether's theorem that symmetry implies a conserved current. So this conserved current manifests itself in terms of the Ward identities, which in turn allow me to convince myself that in any computation, only physical degrees of freedom contribute. So that makes my calculations very meaningful. That is actually something more than that. What is that? this particular Lagrangian that I have written here, J mu A mu, which is psi bar gamma mu psi A mu, this gives rise to a vertex of this variety. So there is an electron coming in, electron going out, and a photon being emitted. So that's the simplest F plus going to I plus gamma that I going to F plus gamma that I'm imagining. I is electron, F is electron, and there is a single photon. So this is being described at the leading order by this particular structure, where U and U bar are simply the spinors describing the electron and the incoming electron and the outgoing electron. Also remember that momentum conservation, which we said was there because of space translation invariance. So we have 4 momentum conservation, in fact, because of space-time translation invariance, which means that if there is an electron coming with momentum p, outgoing electron with a momentum p prime, and a photon going out, I would have p prime plus q equal to p. And the q square, which is a 4 momentum square for a real photon, is 0. So this is what at the leading order, at the tree level. Now in principle, the higher order corrections to the same diagram can change this vertex that I have written here, which was psi bar gamma mu psi, now can change it to psi bar something else which has the same transformation properties under Lorentz transformation. Can I construct more quantities than one which have the same Lorentz transformation properties? And indeed you can show that there are 2. One was this is U bar P prime gamma mu F1, okay. But the other one is U bar P prime and UP sandwiching, in between the sandwiched an operator sigma mu nu, which is gamma mu minus gamma mu, which is just a combination of Dirac matrices. And these Fi's are arbitrary functions of Q square at this point. So this I don't do any detailed calculation. This I just do from symmetry principles again. That if the left-hand side transforms like a 4 vector, the right-hand side must transform like a 4 vector, and I just write symmetry from symmetry. So that you see again the force of symmetry. Now word identity, to lowest order, as I told you, F1 0 is 1, F2 0 is 0. Word identity further guarantees to me, and that is actually a lot of work, that this should be subscript. F1, and by 0 here I mean Q square equal to 0, that is for a real photon. It's equal to 1 to all orders in alpha m equal to E square by 4 pi. Which means that no matter to how many orders you compute, this guy, F1, for an on-shell photon is always 1. And any additional corrections that come only to this momentum structure. This is a very deep result. Why? Let's understand that. Because in this result, when you are deriving this result, more or less you have not used anything other than gauge invariance and current conservation. Which means that this is true not just for an electron, but it's also true for a proton, which is not a point particle. Now in principle you would think that there is a big difference between an electron, which is a point particle, a proton which is made up of quarks and what have you, and a photon when it interacts with a proton will see all kinds of things in it, which it will. But for a real photon, the electromagnetic part of the interaction, the electrostatic part of the interaction is controlled and described by the same number as that of the electron. And actually it's something very important, otherwise our atoms won't be neutral. There might be some small differences because of some higher order corrections. It does not happen. And this is guaranteed to me because of gauge invariance. So this is called, it tells you that the charge of the proton is not corrected by its strong interaction, by its structure. And this is sort of a very important fact, and this is guaranteed to you because of word identities. So that's another very important point, which then I want to use later to show you how it was used to great effect in the development of theory of weak interactions. So I'm trying to tell you these are the things practical physicists learned using Noether's theorem. Now we have to see how they used it. So now I go back to the energy conservation, okay? So energy conservation was known to hold in all theories except for the issues in the context of general theory of relativity, which was mentioned already. And this is story in 1918. And after that, much water flew under the whichever river you like. And to Kurt Gürsey, who is a Turkish mathematical physicist, actually he said that before Noether's theorem, the principle of conservation of energy was somewhat shrouded in mystery. People were giving some alternate frameworks. Mach and Ostwald had actually presented that framework, and at that point there was nothing to refute it. Whereas Noether's theorem conclusively said that it is the space-time symmetries which tell you what should be the conservation laws. So I think that's really Noether's simple and profound mathematical formulation did much to demystify physics. This was his statement. So as I said, her theorem said that all theories which have finite continuous symmetry group, energy conservation was non-negotiable. So that is something you cannot do without. Now, did physicists know any place where energy was not conserved? That's the question, right? Apart from general theory of relativity, which I'm not touching. Indeed, there was one and as you can see, the year is bang in the same year. I mean, those particular decade, I think too many things were happening simultaneously, in fact. So 1918, Chadwick actually noted an apparent violation of energy conservation in radioactive beta decay. So what did he see? Beta decay, we all know. What you see is a nucleus of bismuth converting into a nucleus of polonium, an electron coming out. This is all you see. Now what's the problem? The problem is that the electron has this continuous energy spectrum. Now, there is some mass, there is some energy mass change in this reaction. That is the Q value of the reaction. Then you would say, okay, the electron should have the energy of the Q value, since that's what's all I see. So that means that the energy spectrum should have been here, just one peak. But the energy spectrum is all over the place. So now you can either say that the energy conservation is not valid, or something else is happening. And indeed, now we know that the transition is not like this, but it's a transition of bismuth to polonium with an electron and an antineutron. And you can see here that the data are really pretty conclusive to say that the spectrum is continuous, and you have to realize that the range here is from 0 MeV to 1 MeV. So it's not that you are not able to measure the energy accurately, etc. This is a good experiment which is telling you that if you accept this result, either energy is not conserved. Yes, sir. Yeah. Well, because this is part of the reason, part of what Professor Mukunda was saying, that there are these two different cases of a theorem. And when you have, for example, special theory of relativity and general coordinate transformations, energy is not conserved, but something else is conserved. That was this apparent energy in non-conservation in locally energy was not conserved in general theory of relativity because there was an additional term which was compensating for that. And that is actually the major difference between this and general theory of relativity transformation. So that is the difference between the two cases of Noether's theorem 1 and 2, in fact. So this was the apparent non-conservation of energy. Physicists were really desperate. Bohr has actually written and made a proposal that energy may not be conserved. But the point was that this is like really completely at odds with Noether's theorem, and Noether's theorem by this time was, understood and to be true. And what is important, I think, again, which was today emphasized by Professor Mukunda, that Noether proved the theorem and the inverse too. Converse. Thank you. So it's both ways. If there is a symmetry, there is a conservation law, and if there is a conservation law, there is a symmetry. Which means that if there is no conservation law, there is no symmetry. I think that is also there, and that's a very important point. So therefore, people were indeed, desperate what's happening, and in the Desperation, one of the doyens of theoretical physics, Pauli, actually Wolfgang Pauli, he postulated neutrino production in the process of radioactive decay to actually preserve both conservation of energy as well as angular momentum. because angular momentum conservation comes from rotational invariance, which I have not talked about, but it's understood. And on top of it, the second, which is the exclusion principle that Mr. Pauli, which was very dear to him, because which is what he actually pointed out, that two fermions together behave differently than two integral spin particles. But I'm not going to go into that, but both these were his reasons for, and it was in desperation, because even in his note he says, I really don't like this idea, but I don't see any other way out. So what I'm really trying to say here, and the spin half of the neutrino came from wanting to conserve angular momentum, and his observation was, and this is happening in 1930 now. So from 1918, Chadwick's thing, it took quite some time before physicists actually accepted, or even somebody, and he was not a very shy person, okay? So the point is that even person like him really hesitated for a long time before making a postulate of a new particle, but it was either postulate a new particle or accept energy non-conservation, and energy non-conservation, Emmy Noether was telling us, is a no-no. And actually, very soon after that, 1930 and 1934, Enrico Fermi actually used Pauli's idea and gave the first theory of beta decay. And that is the beginning of theory of weak interactions as we know today. So I mean, I hope I have been able to convey to you how this one single fact literally pushed forward the understanding of particles and interactions among them. And indeed, this is again another beautiful paper, just as much I love Emmy Noether's paper. This is the original paper of Fermi, where he doesn't make an assumption about the neutrino mass. He actually calculates what would be the energy spectrum, and then from that he concludes that it looks safe to assume that the mass of neutrino is close to zero, which it is to indeed even today true. So anyhow, so this is really what I want to show you as an example, how believing in energy conservation led us to a new particle and led us effectively to the theory of weak interactions. So there was another thing which I already told you, that knowing the Lagrangian of quantum electrodynamics, we could derive the word identities. We did derive the electromagnetic currents. We did find that the charge of the electron and the charge of the proton are exactly the same, are not changed by the corrections. Now, Fermi, in fact, in this famous theory, described weak interactions about which at that point absolutely nothing was known, because he was postulating a new interaction. And they were in terms of currents which were very similar to the Noether current, in fact, except for the fact that Noether current of electrodynamics, I showed you, was psi bar gamma mu psi, it was a vector current, whereas the data actually told people that the weak interaction currents can be either vector or axial vector. That is psi bar gamma mu psi or psi bar gamma mu gamma 5 psi. And this is what data told you. And this is where actually Professor Sudarshan and Marshak made seminal contributions, in fact, and I think we should be very truly proud of what they did here. So anyway, this was known, and experiments, and this I think is an important point, the experiments also showed that the weak charge, which was multiplying the vector current for the proton, in fact, was the same as the weak charge of the muon, which was undergoing decay by the same interactions. So now this tells you, just like the electromagnetic charge E, or F10 was the one for both electron and proton, similarly, the weak charge is the same for both proton and for muon, which means that the structure of the proton or the strong interactions of the proton, all sorts of loop corrections, we don't even know it, but we don't need to know it. That is the beauty. And that is the beauty of Noether's theorem. Without knowing the dynamics, you can infer this. And this was actually one of the first steps, first hints that people figured out that there might be a gauge theory description of weak interactions. So now you see, standard model as we know it today is actually the celebration of gauge principles. And the first hint that there might be a unified theory of both weak and electromagnetic interaction came from this, what is called conserved vector current charge. So again, If we didn't know Noether's theorem, we wouldn't be able to conclude this. And of course, the full-fledged developed theory of electromagnetic interactions. Now, the last example that I want to take is actually to my heart very, very dear. It's the fact that in the standard model, I'm sure you have heard people give you popular talks when they say a proton is made up of 2 up quarks and 1 down quark. Up quark has a charge 2/3 the time of the charge of the positron. Down quark has 1/3 the times the charge of an electron. And this looks very strange numbers, but they have been numbers which were abstracted from data by people from a very careful study for various reasons. But now comes the real, according to me, to the force, is that we kind of understand that the quarks and leptons have the electromagnetic charges they have, because if they didn't have those values, the theory will be beset with ill effects of current non-conservation. I want to bring you that point here. Now, what is that? Technical name for this is anomaly cancellation. Sorry, it should be, the spelling is wrong, but okay. Anomaly cancellations, but please read it correct. So, essential for the gauge theory description of the standard model is that it should be renormalizable. Why is that? Because unless it's renormalizable, I cannot calculate corrections in a reliable, controlled fashion in a perturbation expansion. If I cannot calculate corrections, I cannot compare precision measurements with my predictions of the theory, and I cannot test the theory. So renormalizability is the only way we can calculate quantities. It gives me a calculability. So this is extremely important. And what I want to sort of argue and show you is that the requirement of anomaly cancellation uniquely fixes the charges of U and D quark in terms of that of the E. So let me show you how that happens. Or at least not really completely, but I argue. So just go back a step. Let's remind ourselves of gauge invariance. I have tried to give an idea how Noether's theorem led me to the idea that weak interactions should be gauge theories. So gauge invariance requires that the gauge bosons and all the fermions have 0 mass. But the physics properties of the observed weak interactions in the beta decay require these bosons to have large masses, and fermion masses we know are far from 0. We have actually measured them, they are non-zero. So this is reality. But the theory, if these masses are there, won't be gauge invariant. They would spoil the gauge invariance, and hence they would spoil the renormalizability. But this is where Mr. Peter Higgs and other collaborators came to our help. They introduced the idea of spontaneous symmetry breaking and of gauge invariance, particularly of the gauge invariance, and they suggested the Higgs mechanism. So I should actually claim, I hope Shubhro is going to talk about it, that when you start talking about theories with spontaneous symmetry breaking, Noether charge is a very subtle concept and it's not even well defined. That's why I pointed out that for depending on the field configurations at asymptotic distances, Noether charge may even not be defined. But that doesn't matter because the gauge invariance is still preserved for the scattering amplitudes, and nature seems to have used the spontaneous symmetry breaking, so we seem to be happy. LHC has made us happy on that count. But now let me go back one step and see what is the problem. So here, now, we have a theory, which is beautiful. Spontaneous symmetry breaking explains everything, but there is a basic consistency issue with the standard model. What is that? The point is that standard model deals with left-handed and right-handed fermions differently. What is a left-handed fermion? A left-handed fermion is a spin-half particle whose spin is opposite to its direction of motion, and right-handed is whose spin is anti-parallel to its direction of motion. This is rough. There are sort of more better definitions, but this is a simple enough definition which is correct in most cases for our purposes. And standard model deals with them differently. In beta decay, you get only left-handed electrons and right-handed positrons. So that means the right-handed electron don't see the beta decay interaction at all. And this actually causes a problem. Now, why does it cause a problem? So you can show, if you start calculating loops like this, loop diagrams like this, in fact, what happens is if this V1, V2, and V3 are three weak bosons, then these triangle diagrams start having at least one gamma phi. Because I told you there is a vector current, psi bar gamma mu phi, psi, and psi bar gamma mu gamma phi psi. So at each vertex, here I will have psi bar gamma mu psi, for example, but then here I will have psi bar gamma mu gamma phi psi. So I will have at least one vertex with gamma phi. And once I have that gamma phi, actually this loop is infinite and it has a structure which is not present at the tree level in the Lagrangian, which in turn means that you cannot renormalize it, which in turn means the fat is in the fire already again. I mean, you did all these things, you stood on your head, you did spontaneous symmetry breaking, you made the theory renormalizable, and now suddenly this thing has reared its head and says, no, this theory is not well defined. And that's why does this happen? So maybe before I say why does this happen, let me just say for a minute that if we sum over all the quarks and all the leptons of a given family, that is, for example, 3 pairs of up and down quarks of 3 colors, 1 electron and 1 neutrino, as well as all the antiparticles, the coefficient of this infinite term magically goes to 0. Okay, otherwise, nothing. You have to sum over the full generation. So then one finds by demanding that this coefficient is 0. So you write equations. Actually, there are different equations which you arrive at in the charges of the different leptons and charges of the up, down, and electron. So you have 3 equations, and actually you have a unique solution. And that unique solution is the solution that nature has used. For no other values of charges will this anomaly cancel. So there is something really deep about this cancellation of anomaly. There is another point. Here, of course, I should say for this uniqueness of the solution, I have one caveat. In the model, there is no right-handed neutrino. If I include right-handed neutrino, the solution is not unique. Actually, there are different solutions possible. So that, if you wish, is an indirect suggestion that there is perhaps no right-handed neutrino, if you believe in this sort of in the theoretical deductions. So actually, what is another important thing is that the cancellations require that all the members of a given generation of leptons and quarks should be present in the spectrum if some members are already observed in nature for the cancellation to happen. So in fact, historically, when people had not found the top quark and the neutrino of the tau type, and they had only found the tau lepton and the B quark, actually this was a very good reason to look for the top quark and nu tau, because by this time there was enough evidence that gauge theories are indeed the right theories of weak interactions, and therefore people looked for it, so it was a prediction of the theory. So this cancellation of anomalies is actually a very deep and fundamental requirement. In fact, people like Loga and a whole lot of string theorists work on it for gravitational anomalies in a big way on the same thing. So there's something very fundamental about it. Somebody would say, so what? As I already tried to tell you, that these infinities will of course spoil the renormalizability, but where do they come from? They come from a current which is actually conserved at the classical level, and the conservation is spoiled at the quantum level. So the classical field theory will actually have this invariance. Emmy Noether's theorem will tell us that that current is conserved, but at the quantum level it is broken, which means loops will break it. Okay? And there are 2 currents. One is psi bar gamma mu psi, I already talked about it, and other is psi bar gamma mu gamma phi psi. So you have 2 different transformations, psi going to e to the I alpha psi, we already discussed it, and the other one is psi going to e to the I alpha gamma phi psi. And this actually is a funny transformation. It's a symmetry transformation only if the fermions have 0 mass. Otherwise, it's not a symmetry transformation. And further, in the quantum theory, you can show that d mu j mu phi is, so d mu j mu is 0, I told you a few times. But d mu j mu phi is not 0, and in fact, it's proportional to this funny combination of field tensors, and this is the constant completely antisymmetric tensor. So it's a well-defined object, it's non-zero. And as I said, this technical reason for this can be easily understood in the language of functional integral formulation in terms of the non-invariance of the major under transformation. So again, a symmetry thing kind of shows up. So again, to me, this underlies the importance of Noether's theorem all over again. So you can really see that one cannot overemphasize Emmy Noether's contributions to particle physics. I have only taken 3 examples. But I mean, the whole thing, I'm sure by now you're convinced, is that it's there along the way at every step. The theorem and the connection between symmetries and conservation laws have actually guided the development of our current understanding of particles and interaction among them at all steps. But I want to talk about one more legacy of Emmy Noether, and that is the following. You know, in 1932, she gave an invited plenary lecture at the Congress, Mathematics Congress. I have no idea how many women give talks in the ICM that happens these days, most probably very few. And it took close to 80 years when we have the first woman Fields Medalist in 2014. I think this is also legacy of Emmy Noether, for making women believe that yes, this is what can be happening. She is source of inspiration to all the women theoretical physicists and mathematicians, because I think in this area we are still small in number. In other areas they are increasing, but in this area we're reasonably small. And I believe that it was really lucky for the subject and the knowledge that Hilbert, Klein, Einstein, all giants themselves, recognized this giant and mentored her. Because all said and done, howsoever brilliant Emmy was, there is the role of mentoring in your early stages just simply cannot be overlooked. And I personally believe that that is where we lose very often the important women talent, the nurturing in the early days. Apart from Hilbert, who told the colleagues that gender was not relevant as they were seeking an appointment to a university and not a public bathhouse, I think it's really amazing. I mean, for me to think that in 1918, this gentleman was saying this, 1915 actually. But there was Klein, who also said, I'm ashamed to occupy such a preferred position beside Amy, who is far superior to me. I think this shows these gentlemen, very, very highlight where academic achievement was the only merit, that they recognized. And I think that mentoring played a big role, and as I said, we should be really happy. The story also underlines that for a woman, importance of strong family support when she's trying to do this, something which is unusual. She worked without any payment for a long time, and somebody had to support her economically at that point. And it's quite interesting, I found, that even with the support of the doyens like Einstein, Emmy Noether had to be content with a talk, with a lecturer position in a college which was far from the major centers, and she would go every week to Princeton to give lectures. So Princeton was happy to have her give lectures on differential geometry, but they were not happy to give her a job.
And then she used to go to IS, she used to go to Princeton University.
Yeah, you're right. No, you're right actually. No, you're correct. Thanks for correcting me. She actually is on record saying that Princeton University is extremely unfriendly for a woman.
The men.
The men. She actually goes on record. I mean, I have never seen her any other example, but this is a statement she makes very clearly. So, now you wonder, have things changed much? To some extent they have. To some extent they have. But, if I may give a personal anecdote, I remember, I'm no Emmy Noether, but I was told by somebody that my best bet was to teach in a women's college. So somehow we don't seem to get out of that, okay? So things need to some extent they have changed, but we have a long way to go. I still think it's not very uncommon that for a woman scientist, it's perhaps either or choice. For example, Emmy Noether didn't have any personal life. That was a chunk of life that one left out. And that is true for many very significant women scientists of that day. Now things are changing. I think we will all do very well to enhance this part of Emmy Noether's legacy as well. Thank you very much.
few more words about this Mark and Ostwald's. Just a few,
No, Mark I know. Ostwald I don't know actually. Mark's thing I had read quite a few years back. In fact, this was in the context of Abraham Pais's book, so I had read it only in that book. But this had to do with also Mark's general idea of how should I say? I mean, he had these funny ideas, right, about gravitation and stuff. And his basic point was that this local energy conservation, the lack of local energy conservation, is not really to be worried about. And that had to do with his own picture of gravity. So that Ostwald, I have no idea. That's why I actually, if you notice, I quoted a quotation. It's a quotation of Gurse given by Nina Bayer. And Mark I am aware of, but Ostwald I have not the slightest idea. And Mark I know this much, that he basically didn't think that he thought that these three, this I will tell you my source. Source is Abraham Pais's book, where he talked about this. And because he spends quite a long time on how general theory of relativity, the ideas grew. And there basically Mark was at odds with all these three people, saying that there is nothing wrong with local energy being non-conserved. And he has his own way of trying to explain it. So in that sense, he was very much diagonally opposite to the solutions that these people were looking at. Because remember that this is just when Hilbert Einstein action was written, right? So till that point, even that was not clear. So I guess this is all part of that funny era when they were, because even with Einstein's theory of general relativity, something like 4 or 5 years went by when sometimes he had a correct one version, then another version. So it's somewhere along there. Yes, sir.
Apart from Bohr, who was willing to give up energy conservation, Landau also was in the same frame of mind.
Really? I didn't know this.
And then he got into trouble with the orthodox Marxists, communists.
Really? This is very interesting.
Somewhere Engels had said that energy is conserved.
Oh, I see. This I didn't know. But Bohr's I knew because there is a letter which he wrote, in fact. He said that I am now so perturbed by this that I am ready to believe that energy is not conserved.